Warm welcome to everyone. Today, we'll see generally what is machine learning, and we'll jump into further topics like what is simple perceptron, multi-layer perceptron. Okay, just before diving into the topics, uh, like the whole field of machine learning, developed during the World War time. If you see in the World War times, the whole field of machine learning was developing. The reason for that is like most of the algorithms which we use in now in machine learning are developed from the World War times, like because the war was going on and there was huge funding for the defense. So since there are huge funding for the defense, many researchers were working on it, and they were trying to find out decrypt the scripts between the countries. There was war between like British and France, I guess, and British and Germany, British and Russia. And then what happened was there used to be message passing, one secret message from one place to another, like where to attack, when to attack. So so if a British person or something let's attack this part of Germany or attack this part of British. So when the troops were there, one troop will be here, one troop will be here. So each troop should know that, every troop should know that where the next attack is going to be like. So for communication between them, there used to be secret messages, okay, and the messages should be between, like, even though if anyone from other party got in, even though if they got the message, it should be waste. Like from that message, they can't identify anything. Like it will be should be gibberish to them. But for these two people, they should understand it. So during at that time, Britishers were trying to encrypt a system known as IGMA. Like if you guys know, like if you guys have seen Imitation Game or know some perspective about IGMA, like it's a cryptex. Like given a key, it will IGMA will encrypt it. Given a key, it will encrypt it and then it will give the output, like it will be encrypted message. So people were trying to decrypt IGMA. Like if you know Alan Turing, he's like father of computer science. Like actually there is no Nobel medal for computer science. There is no Nobel medal. Like there is no Nobel medal for CS. Like there is only Turing medal. Like if you see other professions like physicist or chemistry or something like biology, they will have Nobel Prize. But for computer scientist and even we have Turing medal. The name Turing came from Alan Turing only. He only proposed can machines think, like that perspective. Like he only proposed can machines thinks. He was the first one to decrypt IGMA. By decrypting IGMA, people have told that he saved more than 20,000 lives in British. I don't know the exact number, but he saved more people by decrypting IGMA. Like before, how he saved is like the message used to be there here, right? He decrypted it. By decrypting it, he knows that next attack is going to be at this place. So people from here used to vacate this place. By this way, he saved many lives. Okay. Next, let's dive into what is neural network. Like first, we'll see a simple perceptron. Okay. Like perceptron will be have inputs. Okay, let's take x1, x2, x3 are the input, and these are the weight 1, weight 2, and weight 3. Okay, and we'll have an output. Okay, just simple perceptron. Inside a perceptron, like what will happen is like x1 multiplied by y1 plus x2 multiplied by w2 plus x3 multiplied by w3, and you will have this weight. This is, and here you will have an activation function, some function, like let's say this is activation function, okay, and you have output y. This is what a simple perceptron is like. You're just taking input, multiplying by weights, and you are getting an output. This is what simple perceptron. Here, like in a machine learning, this we know, inputs, whatever the inputs we know, and y also know. We know at the time of training, initially let's assume that input is there and you have the predicted y, like, okay, this we know, but we don't know the weights. This is what w1, w2, w3, we don't know that, okay. If we take this is generally actually a matrix multiplication only, okay. Yeah, if you know, like if you see, like most lectures, people used to say that neural networks are compared to brain, because when a child was born, they will have very less number of neurons in their brain, like less number of connections between them. As and when they grow, their connections get improved, and there are more connections. Like that's like a biologist perspective of seeing things. But here now, like what actually we are trying to find is like we need to identify the weights in such a way that when matrix X, and this is weight matrix, should be equal to the weight. This is y hat is what we predicted, and y is the original ground truth. The error between this should be less, minimum, okay. This is what actually machine learning is like. Input is there and you have label, and we need to find the weights. This is what machine learning, like we need to find the weights. This is what like machine learning, like you have an input x, you have a function, and you have a output. Like neural networks are known as like function approximators, like, okay. It's a simple perceptron. Everyone understood the architecture, like the simple perceptron, like input is there, weights, and you take these weights, and you at last you apply some activation function. We'll go what are activation function and everything, okay. Next we'll see like what is multi-layer perceptron. Like instead of having a single layer, let's say x1, x2, and x3, there are more neurons, like multiple, more than hidden layers are there, like all are connected. So assume everything is connected, okay. Just for simply I'm drawing this. This is what a multi-layer perceptron is like. You have multiple stack of layers, like this is what multi-layer perceptron. Okay, so what multi-layer perceptron is. Now we'll see like how training actually goes, like in a network. Like you have input x, y, and these are input variables, and you have a single neuron. I will explain from a single perceptron. By that you will be able to capture it. Like initially data, like we will have x and we have labels. These labels are like actual ground truth values, okay. Initially weight will be the we have the input data, and we have the weights w1, W2 W3. Okay, we take X transpose W matrix sigmoid function. This is the Y value. Okay, before that there are multiple activation functions for neural network. Right now consider that this is some function we are getting, and then we are predicting Y, and we got Y, so predicted Y, and this is the actual Y. Okay, the loss, this is the loss. Okay, by comparing this loss, by this loss function only, we will update the weights of W1, W2, W3. Okay, let's first see like what are kinds of loss functions are there. Okay. Mean square error. Okay, it's like you take the whatever predicted one Y, okay, and then ground truth, you take square between them and you average it. This is what MSI, okay, mean square error. And then you have mean absolute error, like instead of having square, you're just taking the absolute value of it. This is what MEAE. Okay, and log loss is like log loss are binary cross entropy. Like you have actual ground truth, and you take log of predicted one, and then 1 minus y, and then you take log of 1 minus p. Okay, I will explain like why there is minus here. Okay, actually this is what log loss is like. Okay, these are some error functions. After finding the loss function, how we are going to update the weights of W1, W2, W3. For that, initially you take stochastic gradient descent. Okay, this one, like how the weights are getting updated is like W equal to weights old, learning rate, whatever is the loss function, and we update this. Okay, this is the next way. Like at first iteration we have this. Okay, at next iteration how the weights are getting updated is like you take the old weight value and then you apply some learning rate is a hyperparameter here. Okay, it can be like 0.0001 or 21. Okay, and you take this loss function, you partial derivate the loss function according to the weights. Okay, like you take these are the loss functions, right? This one are the loss functions. We take this loss function and we differentiate it according to the weight, and we get one value. Okay, this is what known as gradient. Okay, this term is known as gradient. After finding the gradient, we multiply with the learning rate and we update the weights. Okay, this is what happens when you say training a network. Like I'll summarize now everything. Like training a machine learning model is like you're taking the inputs. Initially the weights will be like randomized, random initialization of weights, or any weight can be like these weights will be like W1, W2. It can be 1 or it can be random. Okay, once it randomly initialized, we pass it to a perceptron. After passing from the perceptron, we have the loss function. After finding the loss function, we differentiate it according to each weight, and when we update the weight. Okay, after updation of the weights, what will happen is like at next iteration the loss function, this error term will be less. Okay, this error term should be less. Like initially it won't happen, and after certain iterations the error between the loss function will be less. Like once like at let's say at iteration of 10 and iteration of 11, it's like much more like both are same means we stop training. Okay, it's like there are three important terms like input, weights, and activation function, loss function, and gradient. These are like 5 terms important when we say training a machine learning model. Okay, and we are just updating the weights. For updation of the weights, this is the formula. Okay, when we stop training is like when the error between the next iteration and the current iteration and the next iteration, the if error is less, we stop the training. Okay, by at that time the weights will be like fully optimized. Okay, now let's see like what are activation functions. Okay, before going into the summarize once more time, we have the input data x1, x2, x3, and we have weights w1, w2, w3, and we are taking a transposing and we are doing matrix multiplication of it, and after getting that we will have a single vector value. Okay, and then we are applying some activation function. Okay, and then after applying the activation function, this is what predicted value is, and we are measuring it with the ground truth. By measuring with the ground truth, we have the loss function, and from that loss function we are updating the weights of the neural network. Okay, next let's see like activation function. Okay. What are like activation functions? First one is sigmoid. The value is like 1 plus 1 per e power minus x. Okay, this is the formula for sigmoid activation function. Here x is the term what we predicted, like input w transpose. Okay, sorry, here x is this. Okay, after applying sigmoid function on any input, the value will come to like 0 to 1. Okay, the value will come to like 0 to 1. If you take a sigmoid activation function, right, it will be like a curve like this. Okay, it will be like 0 to 1. Okay, we'll have a curve like this. Okay, after applying sigmoid activation function, you'll get a curve like this. In this curve you can see like the values at the top, right, this one and this one. You can see here like after reaching like if the value is less or if the value is much more, we will try to squeeze the value. Like you can see, even though if in x-axis, this is the x-axis, right, x-axis increases, it doesn't here increase exponentially. If you see here, this increases exponentially, this part. Here it increases exponentially, here and here also. But when we coming to this point, we are trying to squish the value. Like, the reason is like we have done this for like when you find outliers in a point or something, no? Like when there is a huge error in the data or there is outlier, at that time if the distance is more, this point will get squished. Like, to minimize the outliers, the sigmoid activation functions are much useful. Okay, and next, like tan h activation function. Minus 2x minus 1. Okay, this is the tan h activation function here. Okay, this is, you can also rewrite it as 2 into sigmoid 2x minus 1. Okay, once you apply tan h activation function, the value will be reduced to minus 1 to 1. Okay, this is also similar to sigmoid activation function only, but the value will be reduced to minus 1 to 1. Okay, next we will see like ReLU activation function. Whatever is the maximum of 0 to whatever x. Okay, this is the ReLU activation function, 0 to x. Okay, now let's see like how stochastic gradient is. As we see in that, new weight is equal to old weight and a sigmoid activity. Here we are differentiating with respect to loss. See, actually once let's say training a neural network has 3 stages. Okay, first we take the input, we apply weights, and we apply we get the loss function. Okay, we compute the loss. This is known as forward pass. Okay, we have the input, we apply the weight, and then we apply the activation function, and we compute the loss function. This is known as forward pass. Okay, in the backward pass means we are updation of the weights. Backward pass means we are updating the weight. This is known as backward pass. Here if you see, like once the forward pass, when you have a data, you will be having data x1 and label, you will be having from I to n. Okay, from data will be like, you will be having from I data from I to n. Okay, here in this case, in stochastic gradient descent, what happens, like you compute the loss function for summation of y to n. Okay, like you try to understand, I'll make you understand, sorry. Like once the forward pass is done for all the data, you have a data of column of 10. Let's say you have 10 rows. Okay, 10 rows, you have data x and you have y. During the forward pass, what will happen? You take the data and then you apply a forward pass on it. Okay, you compute the loss function. After computing the loss function, this loss will be like for all the data points from 1 to n. So when you see 1 to n means here 1, we have to compute this is like for 1 to n. So when you have, let's say 1 lakh data points, this you have to do for all the weights. Okay, like for one weight, this equation is there. Okay, for one weight, this equation is there. Let's say you have 10,000 weights. Okay, 10,000 parameters weights. Then you have to do this for 10,000 into, you have 10 data point means you have to do this for this many iterations. Okay, so this becomes very huge computationally costly. Okay, what people have batch gradient descent is that's why they came with batch gradient descent. Okay, where you have new weight, the old weight. Okay, and you have loss function. Instead of going from 1 to n, let's say go from 1 to k. Here k can be like 5. Okay, in this data here k can be 5. Do this only for 5 steps, like 5, only for 5, and then you update the gradients, and then you update, like, okay, you guys will generally have a doubt that, okay, yeah, like, that's good. Initially the loss function, let's say in stochastic gradient descent, you have a loss function, right? Let's say you have a loss function which gradually reduces like this. So since you are updating the weights for every iteration, like taking every data point into considering, so you will have a less, like a good curve, like very smooth curve. But when you come to batch gradient descent, you will have a loss function, like here it will pick up, here it will pick up, here it will pick up, some, like, how to say, like some zigzag movement will be there, and then it will smoothen out. Okay, initially it will be there, but it will be smoothening out, but you will get, like, you can do the training in very less time, like time will be preserved. Okay, in batch gradient descent, this is the main difference between stochastic gradient descent and batch gradient. This n and k, these are the two parameters, like these are the two parameters. This is the only difference between batch gradient descent and stochastic gradient descent. Okay. Now let's see another important problem. Like here you are having differentiation, right? Here you are having loss function. You have to compute the loss function. You have to compute the loss function, and you have to update the weight. This is the loss function, right? Like, but when you take these equations, this sigmoid, tan h, these are, like, you can see, like, if you try to like, this looks like a very huge differentiation, right? You have to compute this, and then but actually the people who designed these activation functions have a shortcut that if you differentiate a sigmoid activation function, like if you differentiate a sigmoid activation function, what you will get is a sigmoid activation function only 1 minus sigmoid. Okay, this is what you will get. You try differentiate it. If you differentiate a sigmoid activation function, you get sigmoid 1 minus sigmoid only. You will get this only. Here also, if you, okay, this is like people who designed these equations, this is a shortcut. Like when we apply this over here, right, in the gradient descent, so our computer don't have to do that much computation. Instead of doing calculus, it will just take sigmoid 1 minus sigmoid. This is the differential equation of sigmoid. Like this is a tricks, like, okay. Okay, just I will summarize once more. Training a neural network means you have input data, and you have weights, and you have activation function, and you have a loss function. We are trying to minimize this loss function. Okay, like during 10,000 iteration, 20,000 iteration, the weights are getting updated in such a way that you will have very less loss. Okay, how weights are getting updated in such a way you will have very losses. For that we are using stochastic gradient descent and batch gradient descent algorithms. Okay, for summarization, you have data x and you have weights. Okay, we take multiplication of matrix multiplication of this. Okay, and then we apply sigma activation function. By the activation function we get the predicted value, and we are comparing the predicted value with the actual ground truth. This is known as loss function. Now after the loss function, we are updating the weights by learning rate, and then according to the, we are updating the weights. Okay, after updation of the weights, at the next let's say this is at iteration 1, at next iteration this one is, consider this one as z. Okay, at next iteration z dash, loss function between the predicted value and the actual ground truth value will be less. So z dash will be less than z. This is the our objective. Okay, this is our objective. Should be like it. Initially when you start training, you won't get actually, like there are multiple places, like there are let's say there are saddle points are there, like this point is known as saddle, like this point is known as saddle point. Like when you do the training na, like if you see gradient descent, it will be like here you are having -9 only, right? Like you are trying to go to the less function, like okay, when you are trying here, you are trying to go here the less. In here in saddle point, if you see this iteration and this iteration, after for certain time you will have the same loss function. So model will think that okay, we are predicted, okay, the mod training is done, but actually after some time there is a huge, we can do more training also. This is known as saddle point. Okay, they are known as saddle point. And one more thing, in binary cross entropy here, why here we have minus sign is there, here you can see there is minus sign, right? This minus sign is due to the here this minus sign, okay. If the actual predicted value is less, like this ensures that we are moving down the hill. Okay, like try to imagine how we initially itself we don't know the loss function. How you are saying that this curve will be like this? Like there are so many questions will come in your mind. Like initially itself we don't know that we don't know the loss function. Initially we are in some point here, and how you are sure that we will go to this point? Like right now when studying, try to imagine there is a curve like this, there is a loss function like this, and we are moving towards like this. Okay, we don't know, like, but assume that we know that there is a point like this and we are moving down the loss function like this. Okay, initially itself assume this. Okay, see you in next video.